Welcome to MRL. In this learning session, we'll be learning about rational numbers. Now, what is a rational number? A number of the form p by q, where p and q are integers and q is not equal to 0, is a rational number. Please remember, a number of the form p by q is a rational number. A rational number also can be defined as a ratio of two integers. P is an integer, q is an integer. So take a ratio of p and q, then it is a rational number. Only condition is that q should not be equal to 0. The word rational is derived from the word ratio. The symbol of rational number is q, which is again derived from the word quotient, because p by q gives us a quotient. Now q is equal to, within the braces, x is such that x is of the form p by q, where p and q are integers and q is not equal to 0, is a set of rational numbers. Now if you take natural numbers, 5 is a natural number. 5 can be written as 5 by 1, and therefore 5 being a natural number, it is also a rational number. That means all natural numbers are what we call all natural numbers are rational numbers. So please remember. So also the whole numbers are rational numbers. 0 is a whole number, but 0 can be written as 0 by 1, and therefore every whole number is a rational number. Similarly, integers are rational numbers, because minus 5 is an integer. Minus 5 can be written as minus 5 by 1, because minus 5 by 1 is again minus 5, which is an integer but also a rational number. Therefore every integer is a rational number. Similarly, every fraction is a rational number, and every decimal is also a rational number, because the decimal number 0.2 or any decimal number can be written in the form p by q, which is a rational number. Therefore every decimal number is also a rational number. The conclusion is every natural number, whole number, integers, fractions, decimals are all rational numbers. So if you see here, we can represent the rational number set as a rectangle. That is the Venn diagram here. The rectangle represents the set of rational numbers, and within that we have n, that is natural number set, whole number set, and integer set. This is the geometrical representation of the what we call a set of rational numbers, which we call it as, which is referred to as Venn diagram. Please remember that. Now, positive rational numbers. A rational number in which both the p and q are having the same sign are called as positive rational number. Therefore we say p by q is a positive rational number if p and q have like signs, or signs are same. Negative rational numbers. If p or q, either of them, p or q, if they have a negative what we call sign, then they are negative rational numbers. P by q is a negative rational number if p and q have unlike signs. Now, writing rational number in a standard form. If you are given a rational number 60 by minus 40, the first thing is, you see there is a negative sign in the denominator, which has to be removed. Rather, the denominator has to be made positive, and that can be done by multiplying by minus 1 in both the numerator and the denominator, so that the numerator becomes minus 60, the denominator is minus into minus plus, that it becomes positive, or the denominator has been converted to positive sign. Then minus 60 and 40, they are what? Not co-primes. So we can divide 60 and 40 by their HCF. The HCF of 60 and 40 is 20. So if we divide 60 by 20 and 40 by 20, we get minus 3 by 2. And if you observe here, minus 3 by 2 is in standard form, or it is the simplest form of 60 by minus 40. 3 and 2 are co-primes. That means they have a common factor as 1. Therefore, the procedure is, a rational number p by q is in standard form if q is greater than 0 and p and q are co-primes, or common factor of p and q is 1. Now standard form also is the simplest form of the given rational number. Therefore minus 3 by 2 is the simplest form of 60 by minus 40, or minus 3 by 2 is such that where 3 and 2 are co-primes, 3 and 2 have common factor as 1, and there is no negative sign in the denominator, and this is the standard form, or also the simplest form of the given rational number. You have to follow this procedure to write a given rational number in standard form or in the simplest form. Now what are equivalent rational numbers? Now equivalent rational numbers means the rational numbers which have same simplest forms. Okay, please remember, that means any given rational number or given rational numbers if they have the same simplest form, then they are equivalent rational numbers. Or the rational numbers which have equal cross products are also called as equivalent rational numbers. Let us take an example and understand this. Minus 4 by 3 and minus 16 by 12 are two rational numbers. Now the simplest form of minus 4 by 3 is minus 4 by 3 only, whereas simplest form of minus 16 by 12 will be obtained by dividing the numerator, that is p and q, by their HCF, that is 4, we get minus 4 by 3. And if we observe, minus 4 by 3 is minus 4 by 3, minus 16 by 12 is also minus 4 by 3, therefore minus 4 by 3 and minus 16 by 12 are equivalent rational numbers. So please remember that. Now also, if you take the cross product, minus 4 into 12 is minus 4 into 12 is minus 48, 3 into minus 16 is minus 48, LHS is equal to RHS, cross products are equal, therefore these two rational numbers are equivalent rational numbers. So therefore, to find whether the given rational numbers are equivalent or not, find their simplest forms. If the simplest forms are equal, then they are equivalent, or find their cross products, and if the cross products are equal, then also the rational numbers are equivalent. Now, what is the methods of finding equivalent rational numbers? Now, if you are given a rational number p by q, if you are asked to find out as many equivalent rational numbers, then the method is very simple. Multiply p and q with some non-zero integer, or divide p and q with some non-zero integer to get equivalent rational numbers. Let us consider an example. Minus 4 by 3 is a rational number. We want to find equivalent rational numbers for minus 4 by 3. For that, minus 4 by 3 is, if I multiply by 2 and 2 in the numerator, that is by 2 p and q, then I get minus 8 by 6. So minus 8 by 6 is an equivalent rational number of minus 4 by 3. Multiply 3 by 3 and 3, we get minus 12 by 9. Again, minus 12 by 9 is equivalent rational number of minus 4 by 3. Rather, for minus 4 by 3, minus 8 by 6, minus 12 by 9 are equivalent rational number. Rather, all these three are equivalent rational numbers. So please remember that. Now, equality of rational numbers. Very simple again. If p by q is a rational number and r by s is another rational number, they are equal if they have the same simplest form, or if their cross products are equal. That means p by q and r by s, when simplified, should have the same standard form or the same simplest forms, or their cross products must be equal. That means ps must be equal to qr. Let us consider an example. Now, if minus 44 by 77 and minus 8 by 14 are two rational numbers, the simplest form of minus 44 by 77 is minus 4 by 7, and minus 8 by 14 simplest form is also minus 4 by 7, and therefore these two are equal rational numbers. That is what you have to remember. And also, if I take p by q and r by s, if I take cross product, that is ps and qr, if they are equal, still they are equivalent rational numbers or equal rational numbers. For example, minus 44 by 77 and minus 8 by 14, if I take a cross product, minus 44 into 14 is minus 616, 77 into minus 8 is again minus 616, and therefore the cross products are equal. Therefore, these two rational numbers are equal rational numbers, and please don't forget that. Expressing p by q of required denominator. Now, what is this? Now we have a rational number minus 5 by 8. The 8 is in the denominator, but we want to express this rational number with the denominator of 64. And to do that, very simple, multiply 8 by 8, it becomes 64. But we cannot multiply 8 only in the denominator, we have to multiply in the numerator also. So by multiplying by 8 in the numerator and the denominator, we get minus 5, 8, 40, and 8 into 8 is 64. So minus 40 by 64 is the rational number of which is having a denominator 64. So that is how we can express any given rational number of any required denominator. Now, rational numbers on a number line. A horizontal line which represents rational numbers is a rational numbers number line. That means we draw a horizontal line, take a point representing 0. To the right we have what we call them as positive rational numbers, and to the left we have negative rational numbers. Now, if you observe here, I have taken 0 to 1 I have taken 0 to 1 here, and I have divided into the 0 to 1 into 4 parts, 1, 2, 3, 4 parts. The first part is 1 by 4, second part is half, third part is 3 by 4, and the fourth part is 4 by 4, that is 1. That means we can represent the positive rational numbers, the negative rational numbers on a number line, and therefore a horizontal line which represents rational numbers is known as rational numbers number line. So please remember, on the right side of 0 are positive rational numbers, and on the left side of 0 are negative rational numbers. Every negative rational number is less than 0. Every positive rational number is greater than 0. Every rational number on the right side of a point is greater than the one which is on the left side, and every rational number on the left side is definitely smaller than the rational number which is on the right side. Now, representation of rational numbers on a number line. We are discussing about how to represent the two rational numbers 3 by 5 and minus 3 by 5 on a number line. First, let us draw a number line here. 0 is a point which represents 0 is the point on the number line, and to the right we have to represent the positive rational number. To the left we have to represent the negative rational number. Now, for that, what we have to do, first of all, we know that 3 by 5 is definitely less than 1. That means it lies between 0 and 1. So we have 5 in the denominator. That means we have to make 5 divisions between 0 and 1. We have got 0 by 5 is 0, 1 by 5, 2 by 5, 3 by 5, 4 by 5, and 5 by 5 is 1. And therefore 3 by 5 is there. That means the point P on the number line indicates 3 by 5, which is the rational number on the number line, positive rational number on the number line. And so also minus 3 by 5, again minus 3 by 5 we can represent by taking 5 as the denominator. 0 by 5 is again 0, minus 1 by 5, minus 2 by 5, minus 3 by 5, minus 4 by 5, minus 1. We have divided into 5 divisions here. So minus 3 by 5 represents point Q on the number line, which is minus 3 by 5, and that is how we represent 3 by 5 and minus 3 by 5 on the number line. We can also compare the rational numbers. The comparing means equal to, greater than, or smaller than. So first of all, write rational numbers with positive denominators. Remember how to find out which rational number is greater or smaller. Then for that, write rational numbers with positive denominators. If denominators are unequal, make them equal by taking the LCM of the denominators. Compare their numerators. Compare the numerators. The rational number with greater numerator is always greater. Now let us understand this by a simple example. Let us say we have been given two rational numbers, minus 4 by 9 and 5 by minus 12. Now we have to compare. Compare means find out which is smaller and which is greater. Now first of all, minus 4 by 9, minus 4 by 9 is there. 5 by minus 12, first write it in standard form, because there is negative sign in the denominator. Make the denominator positive by multiplying minus 1 and minus 1 to P and Q. So we have got minus 5 by 12. But here the denominator is 9 for minus 4 by 9, 12 that is a positive 12 for 5 by, that is here it is 12 here. So find out the LCM of 9 and 12, it is 36. So make the denominator 36. To make 36, multiply 4 by 4 and 9 by 4, we get minus 16 by 36, and also 12 into 3 is 36, minus 5 into 3 is 15. So we have two rational numbers with the same denominator, and once we get the rational numbers with same denominator, compare the numerators. Compare minus 16 and minus 15. Minus 16 is definitely less than minus 15, and therefore minus 16 by 36 is less than minus 15 by 36. It means that minus 4 by 9 is less than what? 5 by minus 12, and that is the procedure. The procedure is again very simple. First of all, check the denominators whether they are same. If they are not same, make the denominator same by taking their LCM, and then find the equivalent rational numbers. Compare the numerators. Once you compare the numerators, whichever the numerator is greater, that rational number will be the greater rational number. Now to find rational numbers between two rational numbers. Infinite rational numbers exist between two rational numbers. We can find the required number of rational numbers between two rational numbers by different methods. So let us learn them. Welcome to MRL. This is part 2 of learning of rational numbers. In this part, we'll be learning about the methods of finding rational numbers between two rational numbers and other properties of rational numbers. So let us begin. Methods of finding rational numbers between two rational numbers. There are two different methods. One is called as the mid value method and the other one is known as the denominator method. Now here we are trying to find out the rational numbers, required number of rational numbers between two given rational numbers. If R and S are rational numbers, then the average of R and S, that is adding R plus S divided by 2 is the average, is a rational number between R and S. So that means when I take the average of R and S, I get one rational number R plus S upon 2 between R and S. This procedure can be followed to find any number of rational numbers between two given rational numbers. So let us understand this with the help of an example. Now here we have an example to find 5 rational numbers between 2 by 3 and 8. 2 by 3 is one rational number, 8 by 1 is another rational number. Now to find the average of this, we have to add the two numbers and divide it by 2, and we get, by calculations, we get 13 by 3. And again take 13 by 3 and take 2 by 3. Now find the average of this, we will get 15 by 6. So we have taken 2 by 3 and 8, we have added, we got 13 by 3, we took 13 by 3 and took 2 by 3, we get 15 by 6. Now take 13 by 3 and add 15 by 6, 13 by 3 and add 15 by 6 and divide it by 2, we get 41 by 2. So we have 1 and 2 and 3 rational numbers between 2 by 3 and 8, but we want 5. So let us take now 8 and 13 by 3. 8 and 13 by 3 divided by 2, we get 37 by 6, and take 37 by 6 and 13 by 3, add them and divide by 2, we get 21 by 4. So in all we have 1, 2, 3, 4 and 5 rational numbers between 2 by 3 and 8. It is a very easy method, although it is a lengthy method. Therefore, the 5 required rational numbers between 2 by 3 and 8 are 15 by 6, 41 by 12, 13 by 3, 21 by 4 and 37 by 6. So that is the first method of finding out rational numbers between two given rational numbers. In the second method, that is called as the denominator method. For understanding this, let us consider an example. Let us say we want to find 8 rational numbers between 2 and 3. Here 2 and 3 are two rational numbers. 2 is 2 by 1, one rational number. 3 by 1, another rational number. Now if you observe, here the denominators of 2 is 1, 3 is 1, that means denominators are same. Now for finding out 8 rational numbers, we have to multiply 2 by 9 and 3 by 9. So we get 2 into 9, 1 into 9, that is 18 by 9, 3 into 9, 1 into 9, that is 27 by 9. That means denominators are same. Therefore the required 8 rational numbers are 19 by 9, 20 by 9, 21 by 9, 22 by 9, 23 by 9, 24 by 9, 25 by 9, 26 by 9, and these are the 8 rational numbers between 2 and 3. A very simple method which is called as denominators method, and this was an example when the denominators are same. Now let us consider an example where the denominators are not same, they are different. So let us consider an example. Find 5 rational numbers between 1 by 6 and 5 by 21. Here denominators are different. So now the first step is to make the denominators same, and for that we have to find the LCM of 6 and 21. The LCM of 6 and 21 is 42. So you have to make the denominator 6 as 42. So multiply it by 7. So also multiply the numerator by 7. We get 7 by 42. 5 by 21, make the denominator 42. For that we have to multiply the numerator and denominator by 2. So we get 10 upon 42. So the denominators are same. Once the denominator becomes same, then we have to check whether we can get 5. We will not get 5 here because 7 and 10 we get only 2 rational numbers between 7 by 42 and 10 by 42. So we multiply 7 by 3 and 10 by 3. So we get 7 into 3, 21, 42 into 3, 126, 10 into 3, 30, 42 into 3, 126. Now in between 21 30 we get the required number of rational numbers, that is 5 rational numbers. So therefore the required rational numbers between 1 by 6 and 5 by 21 are 22 by 126, 23 by 126, 24 by 126, 25 by 126 and 26 by 126. Further we can continue, but we require only 5 rational numbers in this. Now the next important topic of our discussion is the operations on rational numbers. When I say operations, very simple, fundamental mathematical operations are addition, subtraction, multiplication and division. So let us begin with the addition of rational numbers. Now when we add two rational numbers, we get again a rational number. The addition is very simple here. The denominators are same, just we have to add the numerators. So minus 5 plus 6 divided by 7 is 1 by 7, which is 100% a rational number. Therefore, addition of two rational numbers when the denominators are same is very simple. Add the numerators and get the answer 1 by 7. Now we can even continue, we can add using a number line. Now on this number line we have minus 5 by 7 on the left side and 6 by 7 on the right side. So now take minus 5 by 7 first. So jump towards minus 5 by 7. From there jump 6 steps. 1, 2, 3, 4, 5 and 6. We get 1 by 7. Same as we follow the rules in addition of integers. Procedure is the same. Only the difference is this number line is a number line of rational numbers. Now addition with different denominators. When the denominators are different, here 5 is different, 5 and 7 are different. So the first step is make the denominator same. 5 into 7, finding LCM, 7 5s are 35. Find the equivalent rational numbers by 5 into 7 is 35, 4 into 7 is minus 28, 7 5s are 35, minus 6 5s are 30. So we have the same denominator 35. So add the numerators, minus 28 minus 30 becomes minus 58 by 35. So that is how the addition of rational numbers is done. The procedure is followed. Now if the rational numbers, if they are mixed fractions like this, then 3 into 2 by 4 addition of minus 6 3 by 2 plus 4 into 1 divided by minus 6, it is mixed. They are mixed fractions. First simplify them, make them improper, that is 4 3 the 12 to the 14 by 4, minus 6 to 12, minus 15 by 2, minus 24, minus 25 by 6. Now add them. Now 4 to 6 are different, denominators are different. So make the denominator same, that is 12, because LCM of 4 to 6 is 12. Now 4 into 3 is 12, 14 into 3 is 42, 2 into 6 is 12, 15 into 6 is minus 90, 6 into 2 is 12, and therefore minus 25 into 2 is 50. Add them. So simplify them, add them, add the sum the numerator, then we get 42 minus 140, which is minus 98 by 12, or minus 49 by 6, and convert it into a mixed fraction. That is how we add the rational numbers. Subtraction of rational numbers is again a very simple procedure. Supposing we have p by q one rational number, r by s is another rational number. Now to add that, find the p by q, take the additive inverse of r by s, that is minus r by s, then add it. Procedure of addition is followed and we get the subtraction of rational numbers. So subtraction of rational numbers is nothing but addition of rational numbers by changing or writing the additive inverse of the subtrahend. So adding of additive inverse of r by s, that is the procedure. Now let us consider an example. 3 by 5 minus 5 by 7. It is nothing but addition of additive inverse of 5 by 7, that is minus 5 by 7. Procedure of addition is followed. Make the denominator same, 35, 5 7s are 35, 5 7s are 35, 3 7s are 21, 7 5s are 35, minus 5 into 5 is minus 25. Add, follow the procedure of addition of integers. 21 minus 25, that is minus 4 by 35, is the subtraction of the two numbers 3 by 5 and minus 5 by 7, which are the rational numbers there. Now multiplication of rational numbers is again a simple procedure. P by q into r by s, multiply the denominators q into s, multiply the numerators p into r. So the product is p into r divided by q into s. So multiply the numerators and denominators and further simplify the rational number which we have got, so that we get in its simplest form. Now for example, 7 by 11 into minus 121 by 14. So multiply 7 into minus 121, 11 into 14, we can simplify here. 11 on the 11, 11 on the 121, 7 on the 7 to the 14, we get minus 11 by 2, or nothing but minus 5 and a half. Another example here, minus 55 by 6 into minus 36 by minus 44 becomes minus 55 by 6, minus divided by minus becomes plus 36 by 44. That means if you simplify it, as we have learned how to cancel the numerator and denominator of fractions, simplify it, minus 15 by 2 becomes minus 7 and a half. Now division of rational numbers. To understand the division of rational numbers, we should know as to what is the reciprocal or multiplicative inverse. If p by q is a rational number and q by p is its reciprocal, please understand, p by q is the rational number and q by p is its reciprocal, means we write the numerator as the denominator and denominator as the numerator here. So p by q is the rational number, q by p is its reciprocal. When we take the product is always 1. Always remember, q by p is the reciprocal of p by q is the reciprocal of q by p. The product of the given rational number and its reciprocal is always 1. Now, if p by q and r by s are two rational numbers, then p by q when divided by r by s, we have to take the reciprocal of r by s, changing the division sign to multiplication. So therefore, the division process converts into multiplication by taking the reciprocal of r by s, that is s by r. So when we multiply the reciprocal of the divisor, we get the product, and that is the division of one rational number with another. Let us take an example. Minus 27 by 24 is a rational number. It has to be divided by minus 18 by 24. Now convert the division into what you call multiplication by taking the reciprocal of minus 18 by 24, that is minus 27 by 24 into 24 by minus 18. When we simplify, we get plus 3 by 2. So that is what is the procedure followed. Now another example, 3 by 2 plus 7 by 4 is one group of rational numbers, and divided by minus 9 by 16 minus 1 by 4, another group of rational numbers. So first of all, solve the bracket following the BODMAS principle. We have to apply the BODMAS here. So 3 by 2, the denominators are different, so therefore we have to take the LCM of 4 and 2, that is 4. So 2 to the 4, 3 to the 6, 4, then 4 on the 4, 7 on the 7, add the numerators here, we get 13 by 4. Similarly here, 16 and 4, LCM is 16. Then we have 16 on the 16 minus 9 on the 9, 4 for the 16 minus 4, add, we get minus 13 by 16. Now division has to be converted into multiplication by taking the reciprocal of the divisor, that is 16 by minus 13, 13 and 13 will cancel, and by simplification we get minus 4. So that is what is the procedure followed, and therefore when we want to carry out the operations on rational numbers, we have to follow the rules of addition, subtraction, multiplication, division, and also the sign rules of integers, and apply the rules of fractions, apply BODMAS so as to get the simplified version of the rational numbers. Now next important topic of our discussion is properties of rational numbers. Now already we have learned about these properties in natural numbers, whole numbers and integers, and all these properties, the properties of integers, as you know, integers are a subset of rational numbers, so all the properties of integers are also closed for a set of rational numbers. But again I have considered here, let us consider as to how these properties are applicable to rational numbers by taking examples. The first important property is the closure property of addition. Addition of rational numbers is a rational number. That means when two rational numbers are added, if we get a rational number, that means the property of that closure property of addition is closed for a set of rational numbers. Let us take an example. 4 by 7 is a rational number, minus 3 by 5 is another rational number, and when we add, we get minus 1 by 35, which is again a rational number. The procedure of addition is followed here. Therefore, closure property of addition is closed for a set of rational numbers. That means when we add two rational numbers, if we get again a rational number, then closure property of addition is closed, and which is true in this case. Now closure property of multiplication. The product of two rational numbers is again a rational number, therefore closure property of multiplication is closed for a set of rational numbers. For example, minus 3 by 5 into minus 7 by 2, we get 21 upon 10, which is again a rational number, therefore closure property of multiplication is closed for a set of rational numbers. Now associative property of addition. Now what is the associative property of addition? When I add b and c to a, and sum of a plus b to c, I get LHS is equal to RHS. That means associative property of addition. Now rational numbers also can be grouped and added in any order. Now for example, you take half 4 by 5 and minus 6 by 7. Let us add 4 by 5 and minus 6 by 7 and then add to half. So I follow the rules of addition of rational numbers and I get 31 by 70. And instead of adding 4 by 5 and minus 6 by 7, let me add half and 4 by 5 first and then add minus 6 by 7 to it. Then we get, by following the rules of addition, again we get 31 upon 70. That means LHS is equal to RHS, and therefore associative property of addition is closed for a set of rational numbers. Now let us take associative property of multiplication. If A, B, C are rational numbers, then B into C when multiplied to A or A into B when multiplied to C, the answer is the same, the value is the same, LHS is equal to RHS. Therefore, rational numbers can be grouped and multiplied in any order, but the result is the same. Now let us take an example. If I consider the three rational numbers 2 by 3, 7 by 8 and 11 by 13 and multiply 7 by 8 and 11 by 13 first and then 2 by 3, I get, following the multiplication procedure, we get 2 by 3 into 7 by 77 by 104 is 77 by 156. So also when I multiply the first two rational numbers with the third, again I get 77 by 156. Therefore associative property of multiplication is also closed for a set of rational numbers. Yeah, come. Welcome to MRL. This is the third part of the study of rational numbers, the properties of rational numbers. Now, in this learning session, we'll be learning about the other properties of rational numbers. Now, let us consider the commutative property of addition of rational numbers. If A and B are rational numbers, then A plus B is equal to B plus A. It means that rational numbers can be added in any order, the sum is the same. Let us consider an example. If I add 8 by 11 and minus 16 by 9, then by following the rules of addition, I'll get minus 104 by 99. Also, if I add minus 16 by 9 plus 8 by 11, again I'll get minus 104 by 99. That means the values are the same. Therefore, commutative property of addition is closed for a set of rational numbers. That means rational numbers can be added in any order, the sum is the same, and therefore the commutative property of addition is closed for a set of rational numbers. Now let us talk about the commutative property of multiplication. If A and B are rational numbers, then A cross B, that means A multiplied by B is same as B multiplied by A. That means rational numbers can be multiplied in any order, the product is the same. Let us take an example. 8 by 11 is a rational number, minus 16 by 9 is another rational number. When we multiply the two rational numbers, we get minus 28 or 128 by 99. So also minus 16 by 9 into 8 by 11, I get minus 128 by 99. Therefore, the commutative property of multiplication is closed for a set of rational numbers. Please remember that. Now let us talk about the distributive property of multiplication over addition. And we know what is distributive property of multiplication over addition. And that is, if A, B and C are three rational numbers, if I add B and C and multiply by A, or multiply A into B plus A into C and then add, the answer is the same. That means LHS is equal to RHS. Let us understand this with an example. Now 2 by 3, 1 by 2 plus 1 by 9 are three rational numbers. Now I have grouped 1 by 2 plus 1 by 9 and multiplied by 2 by 3, followed the procedure of addition and multiplication, and I got 11 by 27. And so also when I take 2 by 3 and multiply by 1 by 2, that is 2 by 3 into 1.5 plus 2 by 3 into 1 by 9, by simplification we get again 11 by 27, that is LHS is equal to RHS. Therefore, it satisfies the distributive property of multiplication over addition, and which is very much closed for a set of rational numbers. Now let us talk about additive identity. Already we know what is additive identity. Additive identity is 0, and here 0 by 1 is a rational number. So A is a rational number, 0 by 1 is a rational number. When we add, we get A. That means when a rational number is added to 0, again we get back the same rational number. Therefore, additive identity is closed for a set of rational numbers. Now coming to the next important property, that is multiplicative identity. We already know the multiplicative identity is 1. If A is a rational number multiplied by 1, again we get back the same rational number, that is A. That means 11 by 12 is a rational number. When multiplied by 1, we get again 11 by 12, and therefore multiplicative identity is closed for, or exists for rational numbers, or is closed for rational numbers. The next important property is additive inverse. We already know what is additive inverse. When A is a number and minus A is its additive inverse, when we add them, that is when A is added to minus A, we get 0. The minus A is additive inverse of A is additive inverse of minus A. So please remember that, and this is closed for a set of rational numbers. Now to understand this, let us take an example. 8 by 13 is a rational number. Its additive inverse is minus 8 by 13. When I add 8 by 13 to minus 8 by 13, I get 0, and therefore additive inverse exists or is closed for a set of rational numbers. Now multiplicative inverse. Again, we know what is multiplicative inverse. We know that if A is a rational number, then 1 by A, that is the reciprocal of A is 1 by A, is called as the multiplicative inverse or reciprocal of A, and when we multiply, we get the product as 1. And mind you, the product 1 is always positive. Now 1 by A is called as the multiplicative inverse of A. The product of rational number and its multiplicative inverse is always plus 1. Please remember, it is always plus 1. For example, 7 by 5 is a rational number. When I multiply by its reciprocal, that is 5 by 7, by changing the numerator and denominator, we get 5 by 7. When we multiply it, we get 35 by 35, which is equal to 1, which is 100% true for a set of rational numbers. Therefore, multiplicative inverse is also closed for a set of rational numbers. So please remember that. Now, the next very important discussion is about types of decimal expansions. We already know what are decimal expansions. Now we have different types of decimal expansions, and they are the terminating decimal expansion, non-terminating recurring decimal expansions, which are two of them, pure and mixed. We'll be learning about it. Then we have the non-terminating, non-recurring decimal expansions. Let us learn one by one and understand them. Now let us consider the first one, that is terminating decimal expansion. So if I have a rational number 2 by 5, if I divide 2 by 5, we get 0.4, and it is ending, that means it is terminating. 0.4 is 100% a terminating decimal expansion. If I take another example, 4 by 125, if I divide 4 by 125, I get 0.032, again it is ending or terminating. So this is called as the terminating decimal expansion. So remember, the decimal expansion which has definite decimal places, there are definite places here, 3 places here, 1 place here, then it is called as a terminating decimal expansion, and therefore 2 by 5 and 4 by 125 are having terminating decimal expansions. And very interestingly, 2 by 5 is a rational number, 4 by 125 is also a rational number. Therefore rational numbers have decimal expansions which are terminating decimal expansions. Please remember that. Now coming to the non-terminating recurring or repeating decimal expansions. If I divide 1 by 3, again is a rational number. 1 by 3 is a rational number. When I divide 1 by 3, I get 0.3333 and less. It continues. It is not ending here. So therefore, instead of writing 0.3333, we put a bar over 3, indicating that it is repeating. And mind you, 0.3 bar belongs to Q. That means 1 by 3, if it belongs to rational number, is a rational number, then 0.3 bar is also a rational number. Very interesting. Therefore, it means it's very clear that decimal expansions which are non-terminating, recurring or repeating also represent rational numbers. The bar above 3 indicates the repeating part. The decimal expansion has indefinite repeating decimals. That means it is an unending here. Therefore, it is called as indefinite repeating decimals, and it is a non-terminating recurring decimal expansion. The decimal expansion after the decimal point here has only repeating part. See, if you observe here, it is a repeating part. After the decimal point, it is repeating 3333, and therefore it is called as a pure decimal expansion. Mind you, it is a non-terminating repeating decimal expansion, but a pure decimal expansion, because exactly after the decimal point there are numbers which are continuously repeating. Let us take one more example. 2.2525. You see here 2525 is called as non-terminating recurring decimal expansion. Here 2525 is repeating, therefore 2.25 bar, and therefore this is what is called as a pure decimal expansion. Now here also 1428557, 1428557 again repeating, that means 0.14257 bar are pure non-terminating repeating decimal expansions. So please remember that. Now let us take an example, 0.256262, and mind you, this is a non-terminating recurring decimal expansion, or definitely a rational number, but you observe a very different thing here. Here 0.25 is not repeating, 6262 is repeating. Therefore, this is a non-repeating part, this is a repeating part. Therefore, this is a decimal expansion which is non-terminating recurring but impure decimal expansion. It's a impure decimal expansion because it has both the non-repeating part and the repeating part. So please remember that. The non-terminating recurring pure decimal expansions and the non-terminating recurring impure decimal expansions, all of them represent rational numbers. Please remember that. Therefore, we can even define decimal what we call rational numbers as a number which has decimal expansions which is terminating or non-terminating recurring pure or mixed decimal expansion, okay, is a rational number. So rational numbers can be defined in two ways. A number of the form p by q where p and q are integers and q is not equal to 0 is a rational number, or we can even say a number which has decimal expansions which are terminating or non-terminating recurring pure or what we call mixed decimal is what is called as a rational number. So please remember that. Now we have the decimal expansions of rational numbers and its parts. The decimal expansions of rational numbers, as we have already learned, has three parts: the integer part, the impure part, and the periodic part. Let us understand this very clearly. Now let us consider the decimal expansion 6.15323232 and so on. Rather, it is 6.1532 bar. Now 6 is the integer part, the first part. The 15 is the impure part, which is a non-repeating part, and 323232 is a periodic part, it is a repeating part. Now if you observe here, the string of digits in periodic part is called as the length of the period. It's called as the length of the period, and the length of the period is 100% is 2 here. It is 2. 1 and 2 is the length of the period. So please remember that. Now let us take one more example. 0.333 is 0.3 bar. It is 100% from after the decimal point only 3 is repeating, and therefore it is it's a pure non-terminating recurring decimal expansion. The length of the period is here 1 and it is purely periodic. Please understand, it is purely periodic. Now let us take this example, 0.00430. Now observe here very carefully, 004 is non-repeating, 0000 is repeating. Therefore we have the non-repeating part, which is called the impure part, and the repeating part, which is having a periodic part or a pure part, and the length of the period is 1. Again, that also represents a rational number. Let us take one more example, 0.153232. Here 15 is non-repeating, 32 is repeating, therefore 32 bar. So therefore this is called as what you call eventually, it is called as eventually periodic. So this is purely periodic, this is eventually periodic, this is also eventually periodic. Therefore remember that the rational numbers have decimal expansions that are terminating, non-terminating purely periodic, and non-terminating eventually periodic. So that is what is some of the important properties of rational numbers we have learnt. So go through all the three parts of the study of rational numbers. In the first part we have studied some properties, second part we have studied some properties, and the third part, which we have just discussed, also has important properties of rational numbers. Please follow the method I have already told you. Please listen to what I speak, read what I have given, and repeat reading and listening, and take a book and note down everything in the book, scribble in the book, so that it will be a reference for you to learn about the rational numbers. So thank you. Good day.